Okay, for better or worse, we're on page 419 now. Um, this is the last problem that we're going to do that's in your homework 28. Problem 52, it is the rotating beacon problem. And if that sounds to you like a classic mathematics problem that many people have solved, that there was an award to solve in some time, well, it's not. But I think it's a cute problem, and in fact, it kind of shows you a phenomenon that I'm sure you've seen before, but maybe you didn't appreciate it, or if you did appreciate it, you didn't quite understand what was going on. This is about. Let me see if I can get the book right here so we can get a picture of this, and I'll draw it again later. Here's the picture right here. This is a fire engine with a beacon on top of it. There are two beams of light, one going this way, one going that way, and a wall. And the beacon is circulating, throwing a spot on the wall. And as the beacon circulates, the spot moves up the wall. And so I'll redraw that in a second. So the question is, if the beacon is rotating at a constant rate, would you expect the spot to move up at a constant rate? And let me show you this laser beam here. I'm going to try to rotate this. I'm going to try to rotate this uniformly. You tell me if you think that spot moved across at a constant rate. Sort of appears to accelerate right down here, doesn't it? Right? I'm rotating at a constant rate, but it appears as it gets further away from the normal position that it moves a little faster. So let's analyze that situation here if we can. Good luck to us. Here is the beacon right here, and here is the wall. And unlike your book, which treats the wall as a building, I'm going to treat this like an infinite wall, because to me this works out a little better if that's the case. Always good to have infinite walls. So I'm going to call beam 1 so we can keep track. This is just one side of the beacon. This is the other side of the beacon. And I've drawn it in a case where the beacon is, the beam 1 is shining normal to this wall here, right? It's as close as it's going to ever be. This distance is 10 feet. The book calls this point A. And then as the beacon rotates, the spot on the wall moves up the wall. And in fact, it moves a distance that we'll call d as a function of time, because as the beacon rotates, the spot moves up the wall at some rate and at some time, and that's what we're all after here. And in fact, the book says if this is 10 feet and this is point A, and at any given time t, the spot is d away, the beam 1 spot is d away. What does this problem look like if the beacon is rotating? I'll have to come up here now. 1 revolution every 2 seconds. 1 revolution every 2 seconds. Well, we've done that before. This is an angular speed, radians per second. But let's get it into radian seconds, and let's do that by saying, well, 1 revolution is 2 pi radians. And there you can see that the angular speed, we're going to call it omega, is pi radians per second. That's omega. Because the next question is that the book is going to ask is, can you model this distance for us here? And I think you can, because if we let this angle, which is a function of time, it opens up as the beam rotates. If we call it omega t, because after all, in t seconds, this angle increases by pi t radians. So we're going to call theta omega t. And then look, the tangent of omega t right, is just the opposite side divided by the adjacent side. D of t all over the adjacent side is 10. And so this function of time, which determines how far away the spot is on this infinite wall from the point A, is given by d of t equals 10 to the omega t. Now your book says d of t is the absolute value of these signs, but I think that introduces problems, and I guess I don't quite get why they've done that. They've asked a number of questions, though. They first asked, can you graph d of t? And we're going to say, you're right, we can. I know what the tangent looks like. And so I'm going to do that real quick here for you. Really wish I had drawn this beforehand, but I didn't. Okay, so let me do this. And what I need is 4 quarter periods. And I'm trying to hurry myself, that's why they're ugly. And 1 period here, if this is, sorry, I said omega t, omega is pi, so I'm going to put that in. Remember that a period is 2 pi all over omega. Omega is pi, so a period is equal to 2 seconds. And that's what this said. This said that there's 1 revolution every 2 seconds. That says the period is 2 seconds. Every 2 seconds, the light does 1 whole revolution. So over here is 2. That makes this 1. That makes this 3 halves. And this makes this 1 half. And what does the tangent do? It starts here until it hits pi over 2, because at pi over 2, while the sine is 1, the cosine is 0. And so d of t looks like this. It shows up from negative infinity, goes to 0, whips up here again, shows up from negative infinity, goes back to 0. Now what is this negative infinity? Well, let's think about it. Is this really d of t versus t? So here we are at time t equals 0, and sure enough, d is equal to 0. And then between time t equals 0 and time t equals 1/2 a second, the beacon rotates and the spot moves up the wall until you get, and continues until you get to pi over 2, and then effectively it leaves the wall, right? Because at pi over 2, it's parallel to the wall, but just past pi over 2, while beam 1 is left the wall, beam 2 shows up here at negative infinity, okay? And then as we continue around to time t equals 1 second, I've now made 1/2 a revolution. Here's beam 1 pointing at the wall, here's beam 1 pointing away from the wall, but at that time beam 2 is pointing directly at the wall, and now it shoots up the wall, right, until it goes just past pi over 2. And then beam 1 shows up down here at negative infinity, okay, and so on. So yeah, pretty reasonable model. Let's look at part B. Part B says, for what values of t is the function undefined? So the answer is at t equals 1/2 and t equals 3/2 seconds, it's going to be, in fact, it's going to be 2n plus 1 all over 2 seconds, ... where n is an integer. And those are the times, again, where the beam is when the beams are parallel to the wall. Yeah? What is C? C says fill in the following table. And you know what? I'm out of space. And I do want to fill in the following table. So I'm going to say goodbye to all this material because the punchline is just now coming up. We got to fill in this table. This table says, let's pick a couple values of t. And let's pick them between 0 and 0.5. Yep. So here are the values of t in seconds. And mind, the first thing that this thing wants is for you to calculate d of t. And so we know at time t equals 0, the distance the distance is 0, okay? And I think I know I've calculated these before, so let me just write these down. At point 1, remember d of t is just 10 tangent pi t. So all I'm doing is putting point 1 in for t and calculating this, this trigonometric form, and I get 3.25, and I get 7.27, and I get 13.76, and I get 30.78. And there, this was part C. And the interesting part maybe comes right here in part D. It wants us to calculate what they called the first differences, but for my God, what they want you to calculate is the average rate of change, right? The average rate of change in each of these little subintervals. Right? At the beginning of this subinterval, the interval from time t equals 0 to time t equals 0.1, function starts out, d of t starts out at 0, it goes up to 3.25, and it did that in 0.1 seconds. So if this is feet, this average rate of change works out to be 32.5. And you're going to find that's in feet per second. Yeah. And let's do the next one. The difference here is 40.20. Between 0.2 and 0.3 is 64.90. Between here and here is 170.2. All right. And these are feet per second. These, in fact, are speeds. These are the speeds at which the dot is moving up the wall, that beam 1 is moving up the wall. For the first tenth of a second, it's moving on average about 32 feet per second. You know, look up from your desk right now, pick yourself up 10 yards or 32 feet. Imagine the spot moving in 1 second across that 32 feet. And then do the same thing for this tenth of a second between 0.3 and 0.4. In the same tenth of a second, it now moves more than 100 feet. More than 100 feet. Now think of something that's 30 yards and then at the same time moves. So it's clearly moving considerably faster, 5 or 6 times, almost 6 times faster than it was in this. So this spot that we saw earlier that kind of moved across and then struck away, well, that's precisely what's going on. The spot is accelerating. And I think what the question D says, the question, this is the answer to D. E says interpret what's going on, and what we're finding here is that the spot accelerates up the wall from t equals 0 to t equals 0.1 second. Now I said that because I unfortunately erased the graph. I'm gonna get it back real quick here. So let's look at why I said initially that I didn't like the way your book treated this by introducing the absolute value. I don't even think it's right. This is 0.5, this is 1. Let's remember what the tangent does. Shoots up like this and then shoots up like this. So this is beam 1 moving up the wall from the point A until beam 1 is parallel to the wall. Yeah. And at that point, this is beam 2. Shows up at the other end of the wall and moves to A. And notice how it moves. It moves fast initially and then slows as it approaches. So it comes down and then slows, and then it'll take off and speed up again. So I think you've actually seen this. If you've seen emergency vehicles and you've seen the reflection, that reflection tends to whip like that rather than move around at a constant rate. So there you go, the infamous problem 52, page 419, more than you wanted to know about rotating beacons.